Hello everyone, my name is Vinicius Matoso and the title of this work is History Matching of Pressure and Temperature Data with the ES-MDA method for reservoir characterization. This work is a preview of my master thesis at LMMP from PUC-Rio and is advised by the Professor Márcio Carvalho and co-advised by the Dr. Damer. The presentation starts with the contextualization of where our work fits in the oil and gas industry. Our work is belong to the Reservoir Management area, and this area has multiple subdivisions. Our projects are inside the reservoir characterization. Here is an example of a well-born reservoir model in which the well tests are commonly used to estimate the reservoir permeates and to make the production potential of the field. Usually, those properties are the permeability in different regions of the reservoir and the porosity. The data viability is essential for the reservoir characterization. Those data can come from different sources and from different times of production. In this work, we'll use the well test before the production starts. The well test consisting of exiting data during a control process of open and close the production valve. Observing this flow plot here, you can understand better how the stats work. When the valve is open, we are producing with this key flow rate, and as a consequence, the pressure starts to decrease until the valve is closed. When the valve is closed, the flow rate is zero and the pressure starts to recover its initial condition. With use of advanced data analysis techniques, the quality of the reservoir properties estimate has increased, contributing to a better production plan of the field. The pressure data are commonly used, but due to the advances in the well sense, the temperature sense have already been installed, and these sensors has a resolution capable of capturing the small variation that occur during the well test. In the oil field, the temperature data is usually used to estimate the production of gas, the leaking along the well, and the formation temperature. However, recent studies show that the temperature transient data can be used to better characterize the reservoir properties. And another important information is that the temperature sensor resolution is better than the pressure resolution. The main goal of this work is to deploy a new methodology for estimating reservoir parameters by using pressure and temperature data. For this, we upgrade our flow simulator to consider heterogeneous permeability and the fluid's properties with the impedance of pressure and temperature. We are validating our flow simulator comparing with a commercial software, and for the inverse problem we are applying the ES-MDA method. In practice, in the first part of the project, we want to simulate a cylindrical reservoir coupled with the well-bore with heterogeneous permeability near the well to provide the pressure and temperature data. In order to simulate a real field data, we are introducing a noise into those simulated data. Given these noises data, we'll solve the second part of the project. For this, the ES-MDA method is applied to estimate the values of the permeability and the porosity, making a history matching with the pressure or temperature data. The first part of the project is a direct problem, in which some assumptions are considered. For example, the model was considered a cylindrical single-layer reservoir with single-phase flow, the fluids are slightly compressible and immiscible, and the flow is governed by the Darcy's law. The reservoir is non-homogeneous, and the well is fully open through the entire reservoir thickness. To solve the direct problem, a finite difference code was developed in MATLAB to solve the mass and energy conservation through the reservoir and the mass, momentum, and energy conservation through the well. In this text, we have some terms that some authors do not consider in order to simplify to solve analytical problems, but in our different method, we are considering all of those terms. The second part of the project is an inverse problem. For it, a non-deterministic method was adopted to give a range of values response. The commonly used methods are the ensemble common filter and the ensemble smoother with multiple data assimilation. The ensemble common filter is an adaptation of the common filter to solve nonlinear problems, while the ensemble smoother with multiple data assimilation is an adaptation to transform the ensemble smoother in an iterative method. Here we have some examples of application of those methods in nonlinear problems. So to decide which method would be applied, we use American-Reynolds work, in which a high nonlinear problem was solved with different ensemble methods, and the ES-MDA presents the better cost-benefit. So how the ES-MDA update process is done? Here is a dynamical sketch of this update process. We have the prior estimate, and as the simulations occur, the prior data get closer to the observed values. The sequence of this sketch is obtained by using this formulation. This formulation takes into account the prior parameters and the relationship between the perturbed observed data and the calculated data. The formula to create the perturbed observed data is this one here. The first results are the validation of the in-house simulator. The Sandface Pressure and Temperature was validated comparing the commercial software using the properties from Onur's and Sinar work, and for the wellhead temperature was validated using the properties from Maurício Galvão. Now will be present the inverse problem results. For this, the in-house code was used to simulate a single porous reservoir with different permeability near the well. The properties of the fluids in the well were taken from Maurício Galvão's work, and the permeability profile is this one. In the first meter we have 50 millidarcies, in the second meter we have 8 millidarcies, and from the second to the end of the reservoir we have the 100 millidarcies of permeability. The well tests were performed consistently in 2 days in a constant flow rate of 800 meter cubics per day, followed by 2 days of static period. To analyze the data that will be used as observed data, the log-log graph was performed for the pressure and temperature data in both periods. Here is the log-log graph for the pressure in the flow period. The reservoir analysis is called heterogeneous graph. And to evaluate the sensibility of the porosity was increased and decreased in 50% the porosity. And to evaluate the permeability, were simulated 3 homogeneous reservoirs using the 3 values of the reservoir analysis. To see the porosity, it is necessary to make a zoom in this region. And as you can see, the porosity making a small effect in the pressure profile. Now, analyzing the temperature data into the flow period, we can observe that porosity has a visual impact into the position of the curve depression, making a zoom you see better. And in observing the final part of the graph, we can see that the heterogeneous profile achieved during a period the flow the 3 permeability regions, which means that the heterogeneous profile has been affected from the 3 permeability zones. Analyzing now the pressure in the static period, we can see that the porosity is still making a small impact in the profile, as you can see making the zoom. And analyzing the temperature in the static period, we see that the porosity is still making a visual impact, but analyzing the end of the curve, we see that the permeability didn't achieve with these 3 different zones. Therefore, our observed data will be the pressure and temperature in the sand phase of the reservoir, considering only the flow period. So, in order to simulate a field data, a Gaussian noise was introduced. For the pressure, was assumed a normal distribution with mean 0 and a standard deviation equal to 15 kPa, and for the temperature, we assumed 2 normal distributions. The first one with the mean equals 0 and the standard deviation equal to 0.005 Kelvin, and the second one 5 times this first one. To perform the ES-MDA analysis, an ensemble of 100 individuals was used, where each individual is a set of log permeability and porosity value. The distribution of this individual for the porosity was made by this normal distribution with mean 0.2 and a standard deviation equal to 0.05, and for the log permeability were created 2 distributions. The first has an is a normal distribution with the mean equal to the expected value, with the standard deviation equal to 0.5, and the other one is also a normal distribution with mean equal to the expected value, but now the standard deviation is equal to 1.0. 4 simulations were performed, and the inflection factor were considered constant and equal to 4. The CD matrix is considered diagonal, and for the pressure we tested two values, and we decided to adopt the 10 kilograms force per centimeter square from Seoul because it achieved the best results in our problem. And for the temperature, we assumed that the CD was composed using the 0.005 Kelvin from Chu et al. These are the results of the pre-testing using the pressure data. The test 1 is considering the standard deviation of the permeability equal to 1, and the test 2 and 3 are considered the standard deviation equal to 0.5 for all the permeabilities. Here is the history matching results. In gray, we have the response of the initial assembly, and in red we have the observed data, and in blue is the result of the test 2. The values of the test 1 and test 3 was also similar to this one, but in order to not pollute this graph, we plot just the test number 2. And here we have the percentual error of each parameters considering the pressure data. And as we can see, the porosity has the highest error. To make a better evaluation of the parameter estimation, here we have the box plot of each variable. And as we can see, the third permeability achieved the best values, with less than 1% of error in the permeability estimation. And the porosity achieved the worst value with more than 5% of error in the porosity estimation. These are the results for the temperature test. In order to evaluate the data, the tests were performed with the same initial assembly used in the pressure analysis, as we can see in this table. And all of the 6 tests achieved similar results in the history match, and as the same reason as the pressure, we plot just the one test to not pollute. And observing the percentual error of the parameters, we can infer that differently from the pressure data, the temperature data can achieve a porosity estimation with less than 5% of error. And to make a better evaluation of the parameter estimation, here we have again the box plot of each variable, and as you can see, the first and the second permeability get the best estimation with less than 1% of error in both values, and the porosity we are achieving a response with less than 5% of error in the estimation. As conclusion of this work, we have the implementation of the transient thermal model for a couple well-born reservoir, the validation with the commercial software, the successful implementation of the ES-MDA method. The pressure and the temperature data can be used to estimate the reservoir parameters. The pressure estimates better the third permeability region, but not achieve a good value into the porosity estimation, and the temperature estimates better the first and the second permeability region, and also the porosity with the less than 5% of error. Finally, I'd like to thank everyone for the attention and acknowledge for those institutes for the financial supports.